All right, today we are going to start our last unit on continuity and limits. To start out with the introduction of limits, we need to go back over what it means for a function to be continuous or not continuous. An easy way to think about whether a function is continuous is if you can draw the function from beginning to end without ever picking up your pencil. So looking at this first graph, would you think that this function is continuous or not continuous? Yes, it should be continuous. It is a line, and a line is a continuous function. What about the next function? No, this one should be not continuous. This is a step function, or that greatest integer function that we talked about earlier in the semester. Can't spell. All right, what about the third one? Yes, this one is continuous. All right, up at the top you will see an address for finding tutorials. Unfortunately, I don't think the videos are working anymore. I can't seem to get it to work in any of my browsers, but if you can get them to work, they are great tutorials to help understand the concepts we're going through over the next few days. All right, so again, what is the difference between a continuous function and a function that is not continuous? Literally, it is, can you pick it up and draw it from beginning to end without picking up your pencil? It does not mean that it has to be continuous for the domain of all real numbers. It just has to be continuous for its domain. So types of continuous functions are all polynomial functions, exponential functions, logarithmic functions, absolute value functions, sine and cosine functions, root functions. And again, like a square root function or logarithmic function does not have a domain of all real numbers. However, from the time I start drawing it to the time I finish drawing it, I never have to pick up my pencil. There are no breaks from the beginning to the end. All right, so what types of functions do have discontinuity? We have three types of discontinuity. We have point discontinuity, we have jump discontinuity, and we have infinite discontinuity. Point discontinuity is when you have a graph that has a hole in it. So it's only discontinuous at one point. So if you think about it back when we were doing our rational functions in Unit 2, sometimes we'd have a graph that would not have a vertical asymptote, a rational function that would not have a vertical asymptote. It would just have a hole in the graph. So that would be point discontinuity. Jump discontinuity occurs like in a step function. So look up the step function up here. When we go from negative, we're at this -1 right here, but we're going on the domain from -2 to 0, we're at a range of -1. And then we jump up, and from 0 to 2, we're at a range of 0. So it actually jumps. You have to pick up your pencil to jump. It's not a vertical asymptote there, it just jumps. Another place we see a lot of jump discontinuity is with piecewise functions. And then the third one is infinite discontinuity. And infinite discontinuity is pretty much when you have a vertical asymptote. When we have a vertical asymptote in the middle of our graph increases without bound or decreases without bound. In other words, it goes off to infinity or to negative infinity. So we call it infinite discontinuity. All right, something else. We have what we call removable versus non-removable discontinuities. If a function is not continuous, its discontinuities can be described as either removable or non-removable. A function contains a removable discontinuity when the value of the function can be defined at the point of discontinuity to make the function continuous. In other words, what that means is if all you have is a hole in the graph, we call that a removable discontinuity because all it would take is one point to make that function continuous. So up here, this situation is a removable discontinuity. However, if you have a jump discontinuity or actual vertical asymptote, it would take a lot more than just one point to make that function continuous. So these are non-removable discontinuities. Now right now you're probably like, why do I care? What does that matter? You'll see when we get into our limits throughout this unit why there's a difference between a removable discontinuity and a non-removable discontinuity. Okay, so for the functions below, what I would like for you to do is, using your previous prerequisite skills, I would like for you to graph each function. If there is discontinuity, state what kind of discontinuity is. Is it point, is it jump, or is it infinite? Discuss whether the discontinuity is removable or non-removable, and discuss whether the function is continuous or not continuous. Go ahead and try the first one. Pause the video, try it. When you're done, turn the video back on. Alright, so pause now. Okay, let's see how you did with this. So if we factor out the numerator, since this is a rational function, that would give us x plus 3 times x minus 2. And in the denominator, we have x plus 3. So in this case scenario, the x plus 3 in the numerator and the denominator reduce. Recall from what we did earlier in the year, that creates a hole when x is equal to negative 3, not a vertical asymptote. Look at what we have left. If we graph what's left, we're technically graphing the line y equals x minus 2. However, it's going to have a hole whenever x was equal to negative 3, because we know x cannot equal negative 3 because we cannot divide by 0. So we're going to graph this line. However, when x is equal to negative 3, we're going to put an open hole in the graph. Of course, if you graph this using your technology, you will not see the hole on the graph, but if you look at the table, when x is negative 3, it will give you an error. So in this case, this one has point discontinuity. And it is a removable discontinuity. And that point discontinuity occurs at x equals negative 3. All right. So try the next one, pause the video, and when you are done, turn it back on. Alright, so what we've got here is a nice piecewise function. So pretty much what we have to do is we graph these functions, but only for the interval that it specifies. So that's why it's called a piecewise function. We're graphing pieces of function to create our function. Guys, one of the things you want to make sure about when you graph a piecewise function, when you're done, it should still be a function. Make sure it passes the vertical line test. If it doesn't, you're doing something wrong. All right, so this first function up here, we're graphing y equals x cubed plus 2, but we're only going to graph that for when x is less than 1. So we would go on our y-axis to 2. This is just our basic cubic function shifted up 2 units. So we go out 1, up 1, back 1, down 1, back 2, down 8, so it would look something like this. However, we only want to graph it up to where x is equal to 1. So when x is equal to 1, we're going to put an open hole because we only want to graph it for when x is less than 1. Sorry, I just said equal to. Only when x is less than 1. All right, then we have to graph the other piece of it. So we're graphing the line y equals negative x plus 1. To help us graph this, we're going to pretend that we're starting here at the y-axis at 1. Then we have a slope of down 1 over 1. So we're going to go down 1 over 1, put a point. Down 1 over 1, put a point. Down 1 over 1. In this case, we're only graphing this for when x is greater than or equal to 1. So we do graph it for x is equal to 1. So that will be a closed hole right there. And then graph the right side. So even though this is not a vertical asymptote what I'm drawing, folks, but if this is the imaginary line where x equals 1, that might help you to be able to draw these. For the cubic function, we're drawing it to the left of that. For the linear function, we're drawing it to the right of that. The cubic function is not equal to 1, so as an open hole, where the linear function is. If they both had closed holes, it wouldn't be a function, because then it would fail the vertical line test. All right, guys, this function is not continuous. Think about it. You have to pick up your pencil to draw it. It has a jump discontinuity in it. So since this has jump discontinuity, it is a non-removable discontinuity. And it has jump discontinuity at the value x equals 1. So this one's non-removable. All right, so try this third one, pause the video, when you're finished, turn it back on. Okay, welcome back. So this third one is another rational function, but in this case, this rational function does not have a hole in the graph because there's not a common factor in the numerator and denominator that reduces. So when we factor out the denominator, there are two values that will make the denominator equal to 0. Therefore, we have two vertical asymptotes, one at -2, x equals -2, and one at x equals +2. We also have a horizontal asymptote. Remember, the horizontal asymptote is not where the function is undefined. The horizontal asymptote is the value that the function approaches as x goes to infinity and negative infinity. So that y equals 0 has nothing to do with whether the function is discontinuous. Because these are vertical asymptotes, it is infinite discontinuity, and they are non-removable. Okay, well, there are two major questions that we want to address today. The first one is, what is a limit? And the second one is, when does it exist and when does it not exist? And we'll actually be exploring these questions for the whole unit. So today we're going to focus on looking at limits from a graphical standpoint and from a numerical standpoint, in other words, using our tables. So starting with this first example, let f of x equal x squared minus 3x minus 4 divided by x plus 1. What is its domain? And sketch a graph of f of x. All right, well, guys, immediately we should recognize that the domain would be all real numbers except for -1. I don't even have to graph that to know that. I know x cannot equal -1 because I cannot divide by 0. So if we set that denominator equal to 0 and solve, we would get x equals -1. So let's just go ahead and note that right here. The domain of this function is all real numbers except -1. X cannot equal -1. We'll just say except -1. All right, if we wanted to graph this function, we would need to factor the function out. So f of x is equal to x plus 1 times x minus 4, all divided by x plus 1. And then we can see, again, that this is one of those cases where we have a common factor in the numerator and denominator. So ultimately, we end up just graphing the line y equals x minus 4. However, we know that x cannot equal -1. So what happens is it ends up being a line with a hole in it. So we can just have a little sketch of that over here real quick. So we have a y-intercept at 4, a slope of +1, and then right here where x is equal to -1, we're going to have an open hole. And remember, all you have to do to figure out exactly where that open hole is substitute -1 into the function where you've already reduced out that factor, and we can see right here -1 minus 4 would be at -5. So what that tells us is this graph has a hole at the point -1, -5. All right, so let's start by looking at a table of values. Pretty much what we would like to do is we want to look at values as we get closer and closer and closer to -1. So it says the table below gives x values that are less than but increasingly closer and closer to -1. These values are said to be approaching -1 from the left. Use your calculator to fill in the missing values of f of x for each x. All right, pause the video and go ahead and fill it in. Okay, I have to use Desmos. You can use your graphing calculator just so you can see. As we substitute these x values into that function, and we're going to use our technology to do it to make it faster, what seems to be happening to these y values? What do they seem to be getting closer and closer to? And you can also see it on the graph. Now be careful, guys. When you look at this graph, you don't see the open hole in it because remember, a point has no definition. But what really, if we could zoom in, which it won't show us because, again, our point has no definition, there is a hole right there. So as x gets closer and closer to -1, what are the y values getting closer and closer to? And hopefully you can see that the y values are approaching the number -5. They are closing in on -5. So we say the y value, or the height we are approaching as we near the x value of -1 in the table above, is called the left-hand limit of -1. It is written as the limit as x approaches -1 from the left. Remember that little negative in the exponent spot means from the left of f of x. So what is the value of the left-hand limit of f of x as x approaches -1? We would say that is equal to -5. Okay, so now what you're going to do is the exact same thing, but this time you're going to find the right-hand limit. So pause the video and use your calculator to find those values, or if you'd rather use Desmos, you can use Desmos, and then fill it out. Guys, if you just copy what we're doing, it's not going to help you when you have to do your assignment. Actually pause the video and see if you can figure this out. Okay, so if we make a table of values and we pick values that are closer and closer to -1, but not actually equal to -1, we can see that our y values get closer and closer to -5. So we say, as x approaches -1 from the right, y approaches -5. Therefore, the right-hand limit, as x approaches -1 of f of x, is equal to -5. So how do the left-hand and the right-hand limits compare? Hopefully you can see they are the same. Therefore, when the left-hand limit and the right-hand limits of f of x as x approaches -1 both exist and are equal, this is important, they have to both exist and they have to be equal to one another. The general limit as x approaches -1 exists is written as the limit as x approaches -1 of f of x, and we would say equals -5. When it's approaching from the left, we put a little negative behind the -1. When it's approaching from the right, we put a little positive there. When you do not see the negative or positive, it's the general limit. All right, so describe in words what a limit is and how it can be found. A limit is where a function intends to go. In other words, it's the intended height of a function, the intended y value, what y value it's trying to get to as x approaches some specific value. So if we're looking at trying to find a limit numerically, what we want to do is choose values of x closer and closer to the x value we're trying to find the limit and see what y value it is approaching. All right, so that seems really weird because you're probably like, well, what do you mean where it intends to go? Because most graphs actually get where they intend to go because most functions are continuous. It's only when functions are discontinuous that you really have to see, are they approaching the same value from the left and from the right? So what we're going to do is now we're going to look at these graphs graphically. So let's go ahead and graph the function y equals x squared plus 1. So it's just our basic parabola shifted up 1 unit. Notice this function is continuous, and it's continuous for the domain of all real numbers. So when that happens, guys, and we want to find a limit at a particular x value, it's definitely going to exist. Because not only does it intend to get to the y value that matches that x value, it actually gets there. So when it says, what is the limit as x approaches 2 of this function, we look, and as x approaches 2, where is this function approaching? It's approaching 5. Not only is it approaching 5, it actually gets there. So we would just say this is equal to 5. Because as x approaches 2 from the left, y approaches 5. As x approaches 2 from the right, y approaches 5. And actually, when x equals 2, y is 5. All right, so look at the next two. Go ahead and graph them and see if you can figure out or think about what the limit would be. And then turn the video back on. Okay, so here's just a basic sine function. The only thing that's changed about this sine function is its period, because it was horizontally shrunk by a factor of 1 over pi. So instead of the period being 2 pi, the period is 2. Other than that, we're just going to graph our sine function. So we set up our graph. Remember, sine always passes through the origin. You have those 4 critical sections, 5 critical points. So pretty much you're graphing what you normally would. It's just instead of putting 2 pi down here, we're putting 2. We graph that one period and then just repeat the pattern to get the rest of our graph. And again, you can always check yourself with your graphing calculator or Desmos. In this case, it wants to find the limit as x approaches -1. So if we look right here at our graph, here's where x equals -1. And you can see as x approaches -1 from the right, y is approaching 0. As x approaches -1 from the left, y is approaching 0. And again, this is a continuous function. So actually, when x reaches -1, y is 0. So the limit as x approaches -1 of this function is 0. All right, finish the last one. Okay, so we've got another rational function. So the first thing we do is factor it apart to see what's happening. And when we factor this rational function, we see the 2's would just reduce. That really doesn't make any difference. But we do have the factor of x minus 2 in the numerator and denominator. Therefore, this function is undefined when x equals 2. However, because that was a common factor in the numerator and denominator, it creates a hole when x is equal to 2, not a vertical asymptote. We also have a vertical asymptote when x equals -1 because we have the factor of x plus 1 only in the denominator. When we reduce everything, we end up graphing just the graph 1 over x plus 1. So that's just our basic rational function, that reciprocal function shifted left 1. So we graph that, and then we make sure that we put our hole where x is equal to 2. Remember, all you got to do to figure out exactly where that point is substitute 2 into your function where you've reduced everything, 1 over 2 plus 1, which becomes 1 over 3. So that's how I knew it was at the point 2 1/3. In this case, it wants us to find the limit as x approaches -1. Well, guys, in this case, because there's a vertical asymptote where x approaches -1, if you look at your left-hand limit, from the left, as x approaches -1, y approaches -infinity. And if you look at it from the right, as x approaches -1, y approaches positive infinity. So first of all, the left-hand limit does not equal the right-hand limit, and in order for a limit to exist, they'd have to be the same. Also, even if both of them were approaching infinity, this limit would still not exist, because in order for a limit to exist, it has to be a number, not an idea. Infinity is not a specific number. It is not a constant. It is a number that keeps increasing and increasing forever and ever. So you can't have a limit be equal to infinity. So in this case, we would say the limit does not exist. And you can just write D and E, but in case you forgot what that means, you might want to write out those words. It does not exist. All right, so in conclusion, when does a limit not exist? There are 2 times a limit does not exist. The first is if f of x is not approaching some constant number, the limit does not exist. So if you see that f of x is approaching infinity at the value you're trying to find the limit for, the limit does not exist. The other is when the left-hand limit is not equal to the right-hand limit. If the left-hand limit is not equal to the right-hand limit, the limit does not exist. So let's go back to the whole removable versus non-removable discontinuities. Pretty much, if you have a hole in the graph where you're trying to find the limit, then that's why that is a removable discontinuity, because the limit does exist. From the left and from the right, you're trying to get to the same intended y value. The only thing that's keeping you from actually reaching it is that hole in the graph. So as long as the left-hand limit equals the right-hand limit, for example, like the very first problem we did, it is okay. A limit will exist if there's just a hole there. However, a limit will not exist if you have a vertical asymptote at the x value where you're trying to find the limit, or if it jumps. So in other words, if you're trying to find a limit where the function is discontinuous and it is a non-removable discontinuity, the limit will not exist. All right, so let's put all this together. So what exactly is a limit? The limit of a function f of x is one number L that f of x becomes arbitrarily close to as x approaches, but does not equal a number c. So I know that's very wordy, so let's put this in symbols. The limit as x approaches c of the function f of x is equal to L. In other words, as x approaches c, y approaches L. Does it actually have to get to L? No. It just has to be closing in on L. So that's why when we're looking at our tables, it has to close in on a specific number. Remember, a limit is the intended height of f of x, where f of x intends to go, where it's trying to get. All right, for each of the following functions below, how does the function value at x equals c, if it exists, relate to the limit of the functions as x approaches c? Use a graph for question A and use a table to do question B. So pause the video, try these. Try the first one graphically, try the second one numerically using a table. When you're done, turn the video back on and I'll explain it to you. Alright, so folks, let's look at this first one. For the first one here, we graph this quadratic function. It gives this the value x equals -3. So pretty much what it's asking us to do is what is the limit of this function as x approaches -3? Well, if you look at it, when x equals -3, it's actually equal, the functional value 0. And if you look at it from the left, as you get closer and closer to the x value of -3, y gets closer and closer to 0. From the right, as we get closer and closer to the x value of -3, y gets closer and closer to 0. Therefore, we can say the limit as x approaches -3 of f of x is equal to 0. Whereas the second one, I used a tabular method. Now guys, the idea is if you're trying to find the limit as x approaches 0, you want to pick x values really, really close to 0. You want to close in on x values close to 0. So when I set up my table in the calculator, I picked numbers. I'm not going to pick like -3, -2, -1. I'm not closing in on 0. I want to pick x values really, really close to 0. All right, so when I'm using my calculator, what I do is I start my calculator at the value I actually want to find the limit, and then I just make the change in table really, really small so I can see x values really, really close to 0. Notice that if you look from the left, it goes like 5,000 and then 20,000. And if you look from the right, it has the same numbers. However, these numbers are getting larger and larger. They're getting further and further away. They're not closing in. They're not approaching a number. Let's look at it at Desmos where we're looking at a few more values. So this is what it means by picking values arbitrarily closer and closer to the x value you're trying to find the limit at. So since it was 0, I went -2, -1, -0.5, -1/4, -1/10, -1/20, -100. I mean, I could even get smaller and smaller. If I wanted right here, I could come and type in, -0.001. But what you see in the y is they're not closing in on a number. They're not converging to a number. They're diverging. Go back to what we learned in the very beginning of the semester. These numbers are getting further and further and further away from each other, not closer and closer and closer together. So they're not converging, they're diverging. Therefore, the limit does not exist. So anytime, as you're trying to find a limit, you notice numerically that the numbers are getting further and further away from each other, that they're diverging, the limit will not exist. And we will just say this is D and E, does not exist. Okay, so now you're going to complete the practice below. Some of them I've set up a table for you already. Some of them you're going to have to set up a table. So like for number 2, use a table to determine the following limits if they exist. Folks, I want to see, you can use Desmos. You can use Desmos. I'd rather use your graphing calculator and play with it because I'm not going to let you use Desmos for the test. But Desmos might be a good thing to use to get comfortable for your exam. Just make sure you can use the graphing calculator too. But maybe show me a little bit of the table so I can see where you worked it out. For 3, I gave you the graph. You're just having to look at it. For 4, same thing. 5 and 6, same thing. Pay attention to if they're left-hand limits versus right-hand limits. And 6, you're going to create a table. So actually show me that table when you complete number 6. And then we will go over this together on Monday. All right, have a